Assalamu alaikum wa rahmatullahi wa barakatuh. Today we are going to present you the mmWave communications, which is prepared by me and my colleagues Omar and Abdurrahman. Why mmWave? The primary reason is due to the expected increase in the capacity demands in the future, maybe for things such as the IoT. Now, to do that, usually we have three different options. First, reduce the cell size, which comes with its own complexity, or we can enhance signal processing technique, but this is not always possible, or we can go to new frequency spectrum, such as the mmWave. But is it feasible or not? If it was feasible, then the capacity will increase. Now, to give you an example, most of the frequency we are using today, or let's say the commercial frequency, are only a small part of the mmWave, which is from 3 gigahertz to 300 gigahertz. Now we will see that mmWave is mostly restricted by the propagation characteristic. First, we have the free space loss, which can be seen from the equation that the frequency is proportional to the free space loss. So as the frequency increases, the loss will increase as well, or the wavelength will decrease, which means the pressure will decrease as well. Hence, we can stack more array of small antennas. Or we can look at even from a different perspective, that if we fix the aperture, then the gain will increase. So for example, if you are using 80 gigahertz instead of 2.4 gigahertz, then it will provide us with additional 30 dB gain. Second, we have the atmospheric attenuation, which is caused by the absorption of O2 and H2O gases. And we can see from the figure that different frequencies are requiring different models since they are treated differently. And for example, for the oxygen, we can see that it's peak at 60 and 119 gigahertz. Last but not least, rain-induced fading, which is caused by the raindrops when its size is comparable to the mmWave size. Hence, it will block it. And to give you some number, for light and heavy rain, the attenuation can go from 2.55 to 20 dB per kilometer. First, we have the foliage attenuation, which comes from the woods and the vegetation presence between the transmitter and receiver that may severely affect the quality of service. Then we have the material penetration, which is obvious. The mmWave frequency cannot propagate well through obstacles. Then we have other propagation factors, such as Doppler spread, which we already know from the lecture, that may cause or that will cause frequency dispersion. Then we have human blockage, and it can go as high as 25 to 3 dB for a single person only. And it makes sense since our body is mostly made out of water.
Modeling mmWave propagation characteristics is challenging, and current channel model suffers from many problems that need to be mitigated first. Some of these problems are lack of measurements. mmWave signals suffer from high attenuation and sparse multipath scattering. The propagation characteristics of a wide mmWave range remain unknown. The 3D models. mmWave systems are expected to apply 3D beamforming, where instead of limiting the beamforming to azimuth dimension, the elevation dimension should be utilized. Bandwidth. The original 3D 3GPP model was designed for supporting the sub-6 GHz band with a maximum of 100 MHz bandwidth. Due to the relatively narrow bandwidth of this model, it is not directly applicable for mmWaves due to their higher operating frequencies and wider bandwidth. Dual mobility is mainly encountered in device-to-device communications with a higher Doppler spread. Directional antennas. The directionality of antennas is essential for mitigating the high signal attenuation experienced in mmWaves. Hence, the effect of directional antennas should be taken into consideration. Large-scale antennas. At mmWave frequencies, high number of antenna elements could be packed into a compact area, which enables the employment of massive MIMOs. The modeling process for mmWave channels started from the simplest models, which were then modified to reach more accurate representation of mmWave characteristics. We start from the reference path loss model, which you are all familiar with, Then we exchange the path loss constant with two new constants to better model both line of sight and non-line of sight characteristics and different scenarios. However, this model was found only practical for propagation distances below 200 meters. Higher ranges are now expected since beamforming is to be used. To adapt with this, a new model was suggested with dual slopes, where the first slope is changed to a second one above a certain threshold distance. A different approach was followed in characterizing the path loss of mmWave signals in the sub 100 GHz band in an outdoor to indoor scenario, which represents the link between an outdoor base station transmitting to an indoor user. This approach argued that the path loss predominantly determined by the material penetration and propagation mechanisms characteristics of the signals, where the path loss increases quadratically with frequency. Hence, a pair of parameters A and B are used for indicating the parabolic behavior of the path loss.
Thank you, Amr. Now let's move to channel model consideration. As we all know, millimeter wave communication systems has no practical application. So all of the work done until this moment was through simulation. So in order to simulate a millimeter wave channel we must take into consideration three main points. The first point is system environment, which can be indoor system, outdoor system, or hybrid system. Moving now to the second point, which is a simulated scenario. As we can see from the two examples here, which is the wireless personal area network and the wireless local area network, are related to the indoor system, while the backhaul is related to the outdoor system. Moving now to the third point, which is the operating frequency, which ranges from 30 GHz up to 300 GHz. Now, how we are going to model the millimeter wave channel? So, here are certain steps that we must follow in order to get with a great model. In the first step, we are going to set up scenario as we saw in the previous slide. In the second step, we are going to set our environment, which is either line of sight or non-line of sight. In the third step, we are going to take a look on the path loss model and the shadowing variance. In the fourth step, we are going to take a look on the large-scale parameters, which contains the number of clusters and angular spreads and delay spreads, as we took in the previous lectures. In this step, we are going to assign a power for each cluster. The step after that will be generating a multipath components for each cluster. Then each component will be assigned a specific power. Then we are going to assign the angle of arrival and the angle of departure, which are the azimuth and derivation angles. After that, we are going to calculate the delays due to the clusters and the multipath components. Then we will assign the antenna polarizations, such as vertical to vertical, horizontal to horizontal, and etc. Then we will generate the channel coefficients as we did in the previous lectures based on the model we used. At the end, we will apply the losses and we will be ready for simulations. Now, here in the last slide, we wanted to give you a flavor of the first subject that we took on E419, which is the link budget analysis. Now, a link budget analysis for a typical millimeter wave communication system would be like this. So basically, our path loss model is this equation here, and our environment is line of sight, and our average shadowing loss is 20 dB, which gave us the free space propagation loss to be 115.32 dB. So our focus here is to get 3.1 gigabits per second of data rate on 0.5 gigahertz of bandwidth. And here are our references.